And thank you for attending today's webinar. My name is Jeff Kenvin, and I'm the Vice President of Science at Micromeritics Instrument Corporation. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We'll try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off of your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available today after the webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Pearl Kwan. I've had the pleasure of working with Pearl since she joined Micromeritics in 2017. Prior to joining Micromeritics, Pearl received her bachelor's degree in chemistry at the University of Georgia, where she studied both chemistry and biochemistry. Her undergraduate research included focusing on X-ray protein crystallography, and since joining Micromeritics, she has focused on both physisorption and chemisorption. Pearl is currently an application scientist at the Micromeritics Norcross headquarters. Pearl, we are so glad you could be here today to share your insights on characterizing advanced battery anodes with gas adsorption, BET surface area, and DFT surface energy.
In this webinar, I'll be presenting on how to characterize a graphite, which is the most frequently used anode material in the current battery industry, using the physisorption technique. Here is the outline of today's presentation. First, I will go over how to obtain the BET surface area for a graphite sample from a nitrogen isotherm. Next, we'll look into how to characterize the ratio of basal plane, prismatic plane, and defects present in a graphite sample using the DFT surface energy method. And then we'll look into the DFT surface energy distribution of different anode materials and see how that compares to the graphite sample. And lastly, I will present a case study done on different graphite-graphene materials, comparing the results from the DFT surface energy to the Raman spectroscopy, which is the method commonly used to characterize the ratio of different planes in graphene or graphite materials. Graphite has a dominating market share as the anode material in the current battery industry due to its relatively low cost, abundance, as well as its functionality such as high energy density, high power density, and long cycle life. Typically, a graphite sample is characterized extensively to gauge its performance with different techniques, including but not limited to BET surface area, porosity, particle size, and density. The image on the right depicts the structure of graphite. By definition, the plane along the lateral axis, consisting of sp2 bonded carbon atoms arranged in hexagon lattice, is called the basal plane. And the plane along the edge of the stack of these graphene sheets is simply called edge plane or prismatic plane. The ratio of these planes are important to be characterized in the context of battery performance. For example, the formation of solid electrolyte interface, also known as the SEI layer, and irreversible charging capacity of lithium-ion batteries are related to the ratio of non-basal plane. With that, it leads to the main characterization method we'll focus on in the scope of this webinar, the nitrogen isotherm. With the nitrogen isotherm, the BET surface area and pore size distribution up to 100 nanometers of a material are most commonly characterized. Typically, from 0.05 to 0.3 relative pressure range is collected for a BET surface area, and 10 to the minus 6 to 0.6 relative pressure range for DFT surface energy. And finally, the full adsorption-desorption isotherm is measured for porosity information. In this webinar, we'll focus on the BET and DFT surface energy methods. Before we discuss about the graphite BET, let's briefly take a look at the background of the BET theory. It stands for Brunauer, Emmett, and Teller, the names of the people who came up with this model. And it was an extension of the Langmuir model that was published in 1932. Langmuir was the one who proposed the idea of using the gas adsorption to calculate the specific surface area using the volume of the single layer of gas adsorbed onto the surface of a material. However, Langmuir assumed that only monolayer formation happens at any given pressure, which is an unrealistic assumption, so BET extended this model to account for multilayer adsorption several years later. In terms of the data reduction, we're looking for the linear region after the knee, which is designated as the point B. The point B indicates where the monolayer is completed and multilayer adsorption begins. Typically, the BET model is well known to be applied in the relative pressure region of 0.05 to 0.3 on a type 2 or type 4 isotherms, which are characteristics of non-porous and macroporous and mesoporous materials. There were several assumptions that were made for the BET theory. First, multilayer adsorption, and then the adsorbent has uniform surface and it's non-porous. Interaction between adsorbed molecules is ignored. Then the heat of adsorption for the first layer is higher than successive layers. And then lastly, heat of adsorption for second and beyond equals the heat of condensation. And with these assumptions, we arrive at the BET equation on the right, where V sub A is quantity adsorbed at a given pressure. V sub M is the monolayer capacity, and P0 is the saturation pressure of the gas, and C is the empirical BET constant. When we linearize the BET equation and plot as a linear plot, the monolayer capacity and the C constant can be calculated from the slope and y-intercept of the BET transform plot. Once the monolayer capacity is calculated, we can calculate the BET surface area by multiplying it with the Avogadro's number and the cross-sectional area of one adsorptive molecule, and normalize this surface area per gram of sample mass. To select the appropriate BET region, we need to find the linear region after the knee of the isotherm, and the relative pressure range can vary sample to sample significantly from the typical 0.05 to 0.3 relative pressure, especially when it comes to microporous materials. To account for this, Roquerol et al. Came up with the Roquerol criteria, and as long as a given set of data meets this criteria for the BET calculations, we have a valid BET surface area. So first, the BT fit should be linear, and C constant should be positive. Then the pressure range should be limited to where n times 1 minus the relative pressure continuously increases with the relative pressure. And the pressure corresponding to the monolayer capacity should be within the selected pressure range. And then the calculated value of the relative pressure corresponding to the monolayer capacity, 1 over square root of C plus 1, should not differ by more than 10% from the value of relative pressure corresponding to the BT monolayer capacity. Here is a nitrogen isotherm and a graphite sample sourced from Sigma Aldrich, collected at 77 Kelvin in liquid nitrogen, measured on the Micromeritics 3-flex. Just immediately looking at the shape of the isotherm, it looks to be the type 2 isotherm, which is a characteristic of either non-porous or macroporous materials. So applying the BT model in the typical relative region of 0.05 to 0.3 P over P0 seems to be appropriate. Here is another isotherm that only collected data points in the BT pressure range analyzed on the TriStar. Here is how the BT data reduction interface looks like on any of our microactive software. And it is easy to see how the selected pressure range meets the Roquerol criteria that are already embedded in the software, displaying the C value, monolayer capacity, and correlation coefficient on the right. Additionally, the Roquerol transform plot is available at the bottom left to easily select the appropriate BT range. The BT plot of the graphite seems unusual from the typical one, and it is more prominently shown on the Roquerol plot, displaying two linear regions from about 0.05 to 0.2 relative pressure, and then another linear region from 0.2 and up. If you're not familiar with a typical BT plot, here is an example of how the BT plot and the Roquerol transform plot look like on a carbon black sample. The carbon black is frequently used as a reference material for phase adsorption, and this particular sample is the non-graphitized sterling FT analyzed on the TriStar. The Roquerol criteria require to select the pressure range up to the apex of the Roquerol transform plot, and with this typical looking Roquerol plot with the shape of increasing concave graph, the maximum is easy to locate. Coming back to the graphite BT, there seems to be a step in the isotherm near 0.2 relative pressure. And the Roquerol transform plot is more prominently showing the step, displaying two linear regions. With no apparent apex in the Roquerol plot, it is not clear where to select the appropriate BT range. Now we can ask ourselves, what is this step in the isotherm that caused the BT plot to have two different linear regions? Looking more closely on the full adsorption-desorption isotherm, collected on the same graphite sample, there seems to be a substep around 0.2 relative pressure and then again at 0.5 relative pressure. And also, when we zoom in into the lower pressure region, there is a more obvious substep at 0.008 relative pressure. And there are different reasons for these substeps observed in the nitrogen isotherm on graphite sample. The first substep at the low pressure region observed at 0.008 relative pressure is reported in the literature to represent what is called the commensurate transition. The nitrogen molecule is known to favorably sit on top of a graphitic ring as depicted on this graphic. And as the pressure increases, the favorable position of the nitrogen molecule is disrupted as more nitrogen molecules are accommodated to adsorb onto the surface, which causes a sudden increase in adsorption undergoing the commensurate transition. Grilla et al. Showed this commensurate transition occurring in relation to the presence of graphitic surface with their microcalorimetric experiments. Here is the differential enthalpies of nitrogen adsorption at 77 Kelvin on sterling carbon black, which was heat treated at different temperatures at 1500, 1700, 2000, 2200, 2700 degrees in Celsius, plotted against the degree of coverage of adsorptive gas on the surface. The second calorimetric peaks showed only for the samples that were heat treated above 2000 degrees Celsius. And those same samples also displayed the substeps in their nitrogen isotherm depicted on the top left graph. They were evidently associated with an increasing in packing density of the adsorptive gas, showing only when the carbon black got graphitized at higher temperatures. The other following substeps that are present in the isotherm are well known as layering transitions, which happen as the nitrogen adsorptive gas adsorbs in the interlayer spacing between the graphite layers. So how does these characteristics apply to choosing the best BET range for graphite? We want to select the pressure range after the commensurate transition and select the first linear region in the typical BET range. The extent of the linear region can vary from sample to sample, so it would be best to report the range of pressure used for BET calculations along with the surface area. Another information we can acquire from a nitrogen isotherm that can be very interesting, especially if you're trying to characterize a graphitized carbon, is from the DFT surface energy method. DFT surface energy method deconvolutes an experimental isotherm into a surface energy distribution based on the library of model isotherms of different surface energies calculated from the density functional theory. On the right is an example of DFT surface energy distribution of silica alumina sample. The incremental surface area is plotted against the adsorptive potential in the unit of Kelvin, which is the surface energy divided by Boltzmann's constant. This method describes the surface heterogeneity in terms of surface area associated with each adsorption potential in the unit of Kelvin. And the colder the temperature, it means that there is less interactions between the surface and the adsorptive molecules. And of course, warmer the temperature, there's more interaction. And the adsorptive potential near 20 Kelvin indicates the gas-to-gas interaction. And the adsorption potential greater than 90 Kelvin indicates the presence of micropores in the sample. Depicted on the bottom left graph, we have a set of model isotherms that were calculated for different surface energies from 20 Kelvin up to 100 Kelvin on non-porous flat surface. We can deconvolute an experimental isotherm with the set of model isotherms to obtain the surface energy distribution of a material. The DFT surface energy method can be really interesting and valuable in the context of characterizing graphite-graphene materials because in 2001, Olivier and Winter associated these different ranges of adsorptive potential to different planes in a graphitized surface. A peak around 50 to 60 Kelvin was associated with the basal plane, and below 50 Kelvin was associated with the edge plane, and finally above 60 Kelvin was associated with the presence of defects in the lattice structure. Shown on the right is the DFT surface energy distribution for the graphitized Stirling FT, which is known to have a very pristine lattice structure. It shows the sharp peak around 60 Kelvin, indicating the exclusive presence of basal plane in the sample. And also in the isotherm, we can see the commensurate transition substep. Here's the DFT surface energy distribution obtained for the graphite anode material. The most of the surface area is distributed around 50 to 60 Kelvin, meaning the most surface area is from the basal plane, and we see some edge planes and defects present below 50 Kelvin and above 60 Kelvin adsorption potential, respectively. Here is an overlay of two additional anode materials, graphene and graphene oxide, sourced from Sigma Aldrich, and both of these showed more surface area than graphite sample. The graphene sample was consisted of prismatic planes and basal plane, but no defects, and the graphene oxide was consisted of prismatic, basal planes, and defects, where the basal plane contributed the most to the total surface area. It also showed some presence of micropores with the peak near 100 Kelvin, and comparatively, the graphene had stronger interactions with nitrogen than graphite anode sample, and graphene oxide exhibited the strongest interactions with the most surface area. Here is the same data shown differently in terms of surface area distribution for each plane. We can distinguish the surface area of each plane for graphite, graphene, and graphene oxide samples very nicely from left to right. The table on the right is the actual surface areas for each plane obtained from the DFT surface energy method. Now I'll present a case study comparing the DFT surface energy to the Raman spectroscopy, which is a well-established method to characterize graphene and graphite, especially for the level of disorder present in a sample. The objective of this case study was to compare the level of disorder measured by the Raman spectroscopy to the ratio of basal plane versus edge plane versus defects measured by the DFT surface energy method in different graphite samples. 3 graphite samples were provided by NeoGraph Solutions. NeoGraph Solutions is a graphite graphene manufacturing company with 140 years of history, and they are a leading graphite solutions manufacturer of natural and synthetic graphite films and foils, as well as a variety of graphite powders, including natural graphite, expanded natural graphite, synthetic graphite, and graphene nanoplatelets. Their applications are in many fields, including but not limited to consumer electronics, electric vehicles, renewable energy, and alternative energy. So we're going to take a look at these 3 samples. The first one is GMP 3000-5, which is an expanded graphite with only few total layer planes with the nominal particle size of 5 microns. The second one is the same series, GMP 3000, but with a nominal particle size of 50 microns. And then lastly, the GMP 1000-20 is the graphite with standard expansion with more layer planes present with nominal particle size of 20 microns. Here is the overlay of nitrogen isotherms of 3 samples obtained from the 3-flex. The sample with the lowest uptake was the GMP 3000-50 in red, followed by GMP 3000-5 in purple, which makes sense since the sample with the smaller particle size has higher surface area. And lastly, GMP 1000-20 had the highest quantity absorbed. On the right, 2 overlay isotherms in log scale demonstrate how many more points were collected by the 3-flex as opposed to the TriStar. As mentioned before, the DFT surface energy method requires collection of really good resolution data down in the low pressure region from about 10 to the minus 6 relative pressure. And on the TriStar, the data were collected from 0.001 relative pressure. Here are the DFT surface energy distribution obtained from the 3-flex on the left and TriStar on the right. And these distributions look pretty comparable, so the TriStar can give an estimated surface energy distribution. But of course, we can see the difference in resolution that the 3-flex offers for prismatic planes and defects around 34 to 50 Kelvin and 60 to 75 Kelvin range, respectively. The graphs for raw Raman data on the left and its normalized version on the right, provided by NeoGraph Solutions. The instrument used to collect this data was Horiba Explorer plus Raman microscope, and then the analysis conditions that were used for this data collection was 100 times long distance working objective, a 532 nanometers laser excitation source, and each spectrum was an average of between 80 to 100 individual targets. On the left is a bar graph that separated each plane according to their respective surface area obtained from the DFT surface energy analysis. It shows the data for GMP 3000-5, GMP 3000-50, and GMP 1000-20 obtained from both the 3-flex and the TriStar from left to right. The data collected from the 3-flex and the TriStar show a really good agreement in terms of the basal plane surface area for each sample. On the right is a table of D to G band ratio obtained from the normalized Raman spectroscopy data that we've seen in the previous slide. The D to G band intensity ratio is known to indicate the level of disorder in the sample, meaning the lower the ratio, the more basal planes are present in the sample as opposed to edge planes or defects. To compare this more visually with the given D to G band ratio, let's look at the percentage bar graph comparing the percentage of each plane in each sample. First, the percentage bar graph shown on the left is the data from the 3-flex, and the right is the data from the TriStar. Even though the TriStar data can seem to follow the general trend, and it can seem to estimate the surface area of the basal plane pretty well, we can't see the resolution of characterizing the defects and the edge planes compared to the data obtained from the 3-flex. Now let's compare the 3-flex DFT surface energy data to the D to G band ratio from the Raman spectroscopy. The lower the D to G band ratio means there is more percentage of the basal plane in the material. For example, GMP 1000-20 with the lowest ratio should have the highest percentage of the basal plane, and that seems to agree well with the data obtained from the DFT surface energy method. However, the GMP 3000-50 has a significantly higher ratio than GMP 3000-5, but when we look at the DFT surface energy data, the GMP 3000-50 seems to have more basal plane than the GMP 3000-5 percentage-wise. Now let's take a look at the actual raw intensity of the D band and G band from the Raman spectroscopy. Interestingly, the Raman signal seems to really reflect the amount of surface area for each plane. GMP 1000-20 shows the highest G band intensity, representing the basal plane in the Raman raw signals, and also the highest surface area of basal plane from the nitrogen isotherm out of the 3 samples. GMP 3000-50 shows the lowest intensity for G band and also the lowest surface area for the basal plane from the nitrogen isotherm. So this case study showed a really good agreement between the DFT surface energy method and the Raman spectroscopy, which is the well-established method in the industry to characterize the level of disorder in a graphitized sample. DFT surface energy can offer the characterization of different planes with a nice agreement to the existing method. With that, here's a list of key points we've discussed in this webinar. First, the appropriate BT region for graphite or graphene materials should really account for different transitions such as commensurate transition or layering transitions. The DFT surface energy method can be used effectively to characterize different planes present in a graphitized sample. And the TriStar can give an approximation, but the low pressure data that can be obtained from the 3-flex is critical for quality DFT surface energy analysis. And lastly, data obtained from Raman spectroscopy is comparable to the DFT surface energy data, especially in the sense of the Raman intensity reflecting the surface area of a given sample. I would like to thank John Southard, who is the research scientist from NeoGraph Solutions, for kindly providing all the graphene graphite materials used for the case study as well as the Raman spectroscopy data, and also for giving me a really good insight into different graphene graphite materials and the general manufacturing processes. If you have any questions on different graphene graphite materials or the Raman spectroscopy data that was presented earlier, please contact him directly at jsouthard@neograph.com. With that, I'll be happy to answer any questions.